Hi, my name is Bryant and I am a development engineer for Texas Multicore Technologies. This video is the second of a three-part tutorial series. In this video, I will be covering the syntax and informal semantics of SequenceL and diving deeper into how to use the language. To get started, we'll take a look at a simple snippet of SequenceL code. The first thing that you may notice is that SequenceL looks very different from other functional languages. SequenceL is a much more modern language, and as such has a much more natural syntax. And if you recall from the last video, the fact that it started out as a self-verifying specification language plays a large role in this. This snippet of code is a basic recursive implementation of factorial. You'll notice the function name, factorial, and a single argument in. The English rating of this function is factorial of n is 1 when n is less than or equal to 1. Otherwise, it is n times factorial of n minus 1. Something you'll probably notice is that there is no return type specified for the function, and there is no type specified for the argument n. Instead, there is a parenthetical 0 after n. This is because SequenceL is an inferred type language. The types of functions and arguments are inferred by their use. The parenthetical 0 is used to denote the depth or dimension of the input argument. This is done ultimately to facilitate a feature of SequenceL we will see towards the end of this video. For now, it's enough to know that scalars are of depth 0, lists of scalars are of depth 1, lists of scalars are of depth 2, and so on. Since SequenceL compiles to C++, it supports very similar data types. SequenceL supports integers, floats, characters, and booleans, and all of these are scalars, which are of depth 0. SequenceL also supports the non-scalar data type list. Lists are formed using square brackets. Double quote string syntax can be used as a shorthand for lists of characters. SequenceL also supports structs, which are considered scalars and are of depth 0. These structs are similar to the structs present in C++. They allow developers to logically group related data into a single data structure. Members of structs are accessed using the dot operator. Here we see some examples of using structs. First, we have num1 defined to be a struct with a real member equal to 5.4 and an imaginary member equal to 3.2. Next, num2 is defined to be a struct with a real member equal to 1.3 and an imaginary member equal to negative 2.7. In the definition of main, you can see that we can access the members of num1 and num2 using the dot operator. SequenceL supports the standard arithmetic and Boolean operators, like addition, subtraction, multiplication, division, exponentiation, and modulus. SequenceL, however, uses the word mod instead of the % for modulus. This again traces back to its origins as a specification language and the desire for readability. You'll also notice that SequenceL uses a single equal sign for equality and slash equals for not equal, and plain text and or and not as logical connectives. Again, all in favor of readability. SequenceL has a built-in list concatenation operator denoted by two adjacent plus signs. Here we see x defined to be the list 1, 2, 3, and the list y defined to be 4, 5, 6. X plus y is the list obtained by concatenating x and y and results in the list 1, 2, 3, 4, 5, 6. List concatenation also works on higher dimension lists. For example, next we see the 2D lists A and B. A plus B is the larger 2D list obtained by putting the rows of A and B together into the same list. SequenceL also has a built-in list generation operator denoted by an ellipsis. Most modern languages support an operator to generate lists of integers, and SequenceL's ellipsis operator functions similarly to those, generating a list of integers ranging between its two operands inclusively. Here we see x defined to be 5, 9, which gives us the list 5, 6, 7, 8, 9. Here we can also look at how to index lists in SequenceL. Square brackets are used to index lists in SequenceL, as with most modern languages, with one key difference. SequenceL uses 1-based indexing instead of 0, again, tracing back to its origins as a specification language. So here we see x indexed with 2 is 6, In SequenceL, you can also index lists using lists of integers. Here we see x indexed with the list 2, 1, 4, 3. This gives us the second, first, fourth, and third elements of x in that order, so we get the list 6, 5, 8, 7. This has the side effect of SequenceL having a built-in slicing or sublist operator. X indexed with 2, 4 gives us the list of the second through the fourth elements of x, 6, 7, and 8. Next, we'll look at a more unique operator in SequenceL, the all keyword. The all keyword is used as an index and allows the developer to index every element in a given dimension of a list. For an example, we'll look at the 2D list x, defined to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Indexing x with all, 2 specifies that we want all rows of x in the second column, which results in the list containing the second column of x, 2, 5, 8. If we index x using all, 1, 2, that specifies that we want every row of x in the first through the second column. This results in the 2D list containing 1, 2, 4, 5, and 7, 8. Since indexing a 2D list in SequenceL with a single index returns the entire sublist at that position, using the all keyword as the last index has no effect. This can be seen in the last two examples here. Here we see some of the built-in functions of SequenceL. Again, in favor of a simple language, SequenceL has very few built-in functions. Anything more is shipped as separate libraries to be included. Next, we will look at how to define functions in SequenceL. To do this, we will be looking at an example function which implements the quadratic formula. If you've forgotten the quadratic formula since school, we have it here for reference. Recall this formula calculates the two real roots of a quadratic equation, and that the expression under the square root is referred to as the discriminant. To get started, we see the function name quadratic and the argument list with the depth specified. This function takes 3 arguments, all of which are scalars, of depth 0. Next, we'll look at the body of the function. The English reading of this function is, the real roots of the quadratic equation, defined by a, b, and c, are root 1 when the discriminant is 0, root 1 and root 2 when the discriminant is greater than 0, and there are no real roots otherwise. Next, we have the let body, which lets us define local variables. You'll notice that if the discriminant is less than 0, the definitions of root 1 and root 2 will attempt to square root a negative number, causing a runtime error. However, statements in a let body are only executed as needed and at most only once. For example, if discriminant is less than 0, neither root 1 nor root 2 are computed, since neither are needed. If discriminant is equal to 0, only root 1 is computed, since root 2 is not needed. This can be thought of as automatically wrapping all local variables in executability checking statements. The let body also has the added benefit of bridging the gap between procedural and functional programming, as it allows for pseudo-procedural computations that still benefit from SequenceL's performance. Now, we will get into some of the more unique features of SequenceL that really distinguish it as a language. The inventors of SequenceL noticed that algorithms spend a lot of time iterating non-scalars, things like arrays and matrices, both in development of the algorithms and actual execution of the algorithm. The first thing a developer thinks of when presented with a simple problem to solve is usually the looping necessary to solve the problem. And then during execution, the algorithm spends a lot of time iterating to break down the input data and put it back together as output. SequenceL attempts to eliminate the need for loops to iterate non-scalars with 2 key features, index functions and normalized transpose. The first of these features that we will be looking at is the index function, sometimes called free variables. These are similar to the free variables in mathematics, which allow you to define the elements of a list in terms of their positions. Something like x sub I is equal to I plus 1. In SequenceL, functions that return a list can be defined element-wise in terms of what value should be at a given index. We see an example of this here with the function replace. Replace takes 3 arguments, v, which is a list of depth 1, and 2 scalars, x and y. The first difference we see here is the bracket I at the end of the function definition. This indicates that the function is a 1D index function and its free variable is I. The English reading of this function is, the ith element of the result is y, when the ith element of v is x, otherwise it's the ith element of v, replacing every occurrence of x in v with y. You'll notice that the range of I is never defined. This is because SequenceL detects that I is used to index v, and infers that I should therefore range from 1 to the size of v. Here we have some more examples of defining index functions. First, we have the function unit vector, which returns the nth unit vector of length L, or the list of length L which contains all zeros except in the nth position, which is a 1. This function can be read as, the ith element of the result is 1 if I is n, otherwise it is 0. You'll notice here that we don't use I to index anything in the body of the function. SequenceL is unable, therefore, to infer the range of I. In cases like this, the developer must explicitly state the range of I using the for each statement. Here, I ranges from 1 to L. Next, we have the function ID matrix, which returns the n by n identity matrix, or the 2D list which has 1s on the diagonal and 0s elsewhere. You'll notice that this function makes use of two free variables since it is defining a 2D list. This function is read as the element at I, j is 1 when I is equal to j, and is 0 otherwise. Again, the range of I and j must be specified. The ranges of free variables can also be explicitly defined when the developer would like to overwrite the inferred range. Next, we will look at normalized transpose, sometimes called overtyping. But first, a quick reminder about depth. Remember that scalars are of depth 0, lists of scalars are of depth 1, lists of scalars are of depth 2, and so on. Normalized transpose allows us to apply a function to find an argument of one depth, element-wise, to a list of arguments of that depth. The function is applied to each member of the list, possibly in parallel, and the results are recombined into the resultant list. Here we see some examples of using normalized transpose. First, we see adding 10 to the list 1, 2, 3. The addition operator is overtyped and results in the list 11, 12, 13. Next, we see the function absolute value being overtyped with the list -3 through 3. This results in the list 3, 2, 1, 0, 1, 2, 3. Normalized transpose also works on user-defined functions. If you'll recall, we defined the function replace to take a list and two scalars as arguments. Here, we are calling the function with a 2D list as the first argument. This function call will normalize transpose and result in applying replace C with Z on ABC, and then applying replace C with Z on CDE. Earlier, I pointed out that SequenceL has very few built-in functions. This was, in part, facilitated by normalized transpose, which allows developers to easily write things that are commonly built-in functions. First, we'll look at vector addition. If a developer wanted to write a function which adds two lists, U and V, they would simply add U and V together. The addition will normalize transpose and result in the element-wise addition of U and V. Next, we have the vector dot product, which is the sum of the element-wise product of two vectors. The dot product of the lists U and V can be written simply as the sum of the products of U and V. Here, the multiplication will normalize transpose, resulting in the element-wise product of U and V, and we can simply sum the resulting list. Finally, to see an example of normalized transpose on a high dimension, we can look at the matrix row sum. To write a function which, given a 2D list A, returns a list containing the sum of each sublist of A, we can simply use the sum function. Passing the 2D A to sum will normalize transpose and apply sum to each sublist of A. Now, aside from a few built-in functions, that is the entire language of SequenceL. It is, by design, a simple and straightforward language. Simon Peyton Jones, in 2002, said that any language large enough to be useful must be dauntingly complex, while Dr. Daniel Cook, the inventor of SequenceL, said no it doesn't. SequenceL is his proof that a useful language need not be dauntingly complex. In the next video in this series, I will explore some anecdotal evidence of the read and write ability of SequenceL, as well as the effects of autoparallelization. Thank you for taking the time to watch this video. If you have any questions or comments, feel free to comment on this video or contact us via our website, which is linked to in the video description. If you're interested in learning more about SequenceL, be sure to subscribe to this channel.